Hello all, my name is Ashutosh. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, in this particular lecture, we will going to discuss about compounding in pulse code modulation. So these are the outlines. We'll start up with the introduction where we will try to discuss some of the problems associated with the linear quantization in pulse code modulation. Then we will devise up how we can rectify those problems with the help of compounding. Obviously, while discussing what is compounding, then we will discuss A-Law of Companding and one numerical associated with that A-Law of Companding. Then we will discuss mu law of compounding, which will be followed by a numerical problem. And finally, we will going to conclude by sharing some of the importance of compounding. So in our last lecture, we have evaluated the signal to quantization noise ratio for the linear quantization in the PCM systems. We have evaluated that the quantization noise power would have been evaluated as delta square upon 12 and signal to noise ratio in dB would have been given as 4.8 plus 6n, where n is the number of bits required to encode a sample. So in linear quantization, we'll be having two major drawbacks. What are they? The uniform step size means that the weak analog signal will have a much poorer signal to quantization noise ratio than the strong signals. What I'm trying to say here is if the signal power is low, then the signal to quantization noise value will be deteriorated much in comparison to the strong signals or those signals which will be having some high amplitude. As we know that signal to noise ratio is nothing but it's the ratio of signal power to the noise power. So obviously, if the strength of our signal is lower, then the signal to noise ratio will be inferior in comparison to the signal to noise ratio where the signal power is higher. And second most important drawback is a system-wide dynamic range require many ending bits and consequently wide system bandwidth. Obviously, if the amplitude excursion is higher, then in order to map those amplitude levels, we must be requiring higher number of levels and higher number of levels consequently required a larger number of bits to encode any individual sample. So obviously, if the input range is higher, then we'll be requiring larger number of bits, which consequently demands higher amount of bandwidth. These two are the major drawbacks that we have in our linear quantizing PCM systems. So how can we overcome them? So the solution is compounding. So now the question is, what is compounding in pulse code modulation system? Compounding is nothing but it is the process of compressing and the expanding of signal while encoding and decoding process. So what we are actually trying to do in compounding is we will going to compress our signal when the signal strength is higher, and we will going to expand our signal strength when it is having lower amplitude values. So obviously, if we will going to expand our lower amplitude values, the signal to noise ratio will be improved. In other words, we could also define compounding as it is the non-uniform, or we could say non-linear encoding decoding process is called compounding. So in uniform quantizer, we will be having uniform step size delta, whereas in the non-uniform compounding, we could have variable step size delta. So this we have discussed that it could obviously enhance or improve the signal to noise ratio when the amplitude level is lower. So how we are actually going to perform this non-uniform encoding? So before we discuss, let us first understand the working of compressor via input-output transfer characteristics of a quantizer. So this particular figure shows the input-output characteristics of a quantizer. On this x-axis, we will be having input to the quantizer, and on the y-axis, we will be having the output of the quantizer. So this particular straight line is actually being shown the linear relationship between the input and output. Suppose we are providing Vmax as an input, so at the output we'll be having V0 of max, and for this minimum value of input we'll be having V0 minimum. So the relationship between the input and output will always be a linear one. I mean, if we will be having this much amount of input, then the output will going to lie somewhere here. So this particular figure is basically without any sort of compression. We'll be having linear relationship between the input and output. So with the help of compressor, what we are actually trying to do is this type of input output relationship we will going to achieve with the help of compressor. I mean, for lower amplitude values of our signal, we'll be having some higher amount of amplitude level of our signal, so that we could have some better characteristics in comparison to signal to noise ratio. So I mean, at lower values of input, we will going to expand our signal. So at the transmitting side, we will going to do that, and at the receiving side we have to perform this inverse operation. So this is our compressor characteristics, which is a non-linear one. That is why it is also being called as non-linear compressing. So for this value of input, if we are using linear quantization, then the compressor output will lie going to somewhere here. But since we are using nonlinear compounding, so at lower input level, the output level would be subsequently larger one. That means over this compressor, the output will be much higher. The amplitude level lies going to be here in place of here. So we could say that via applying this nonlinear compressor characteristics, we will going to subsequently improve the signal to noise ratio. So when the input signal is here, then the output of our quantizer will going to lie over here. And at this level of input, we will be having this output level. But if we are using linear quantization, that output will going to lie somewhere over here. So we can say that we had improved the signal to quantization noise ratio. So now we will going to discuss how we will going to perform this non-linear compression. So there has to be certain rules and standards that we have to follow. So basically compounding is mainly of two types. Number one is A-Law of Companding and second one is mu law of compounding. So at different regions, we'll be using different types of compounding schemes. For example, mu law of compounding would have been used at America and Canada, whereas A law of compounding would have been used in European countries. So now we're going to discuss those standards one by one. Start up with A law of compounding. So what is A law of compounding? A law of compounding would have been performed by A law of compressor, and the compressor characteristics is piecewise. I mean, it is not continuous. It is made up of linear segment for low value of inputs, and for high value of inputs we'll be having some logarithmic scaling. So the logarithmic compressor standard uses in European telecommunication system, as we have already mentioned, and the characteristics of that logarithmic compressor would have been given as y is equal to 1 plus ln a times of s, 1 plus ln a sine of s, where this s will lying between 1 and 1 by a. So obviously we need to memorize those characteristics as these are standards. Obviously I'm going to discuss what is this A, S and Y. So Y is nothing but it is the normalized output signal, and this S is normalized input signal. A is a standard. So what these characteristics actually being showing is, if our normalized signal strength will lying between 1 by A and 1, then the output of the compressor or the normalized output of the compressor would have been given by this particular equation. And if the normalized signal value will going to lie in between 0 and 1 by a, then the output or the normalized output of the compressor would have been given by this particular equation, a times of normalized value of our signal over 1 plus ln of a sine of s, where this sine of s is actually being showing as the sign of our signal, that is whether it is negative, positive or 0. For negative, we'll be having this sign of s would have been termed as -1, and if our signal value is positive, then the output of this sign of s will be a positive one, and if it is 0, then its value will be 0. and A is the constant. It is a well-defined standard and it has been chosen as 87.56. So as we had already discussed, S will going to give you the normalized input. We had already mentioned how to calculate the normalized signal. We just have to divide our signal with its maximum value, and Y is the normalized output and A is the parameter that has been selected to give the desired compressor characteristics, and it has been given as 87.56. This is a standard result. This I had also discussed. The sine function returns -1, 0 or +1 when the numerical expression value is negative, 0 or positive respectively. Obviously I'm talking about the signal value. If it is negative, then the outcome of this sine function will be -1. If it is positive one, then its output will be a +1, and if it is 0, then it returns a 0. So now we're going to discuss a numerical problem over A-Law of Compounding. So the question says an A-Law quantizer or compressor has an input range -5 volt to +5 volt. For A is equal to 100, find the output of the quantizer for the inputs of 30 millivolt and 3 volt. So the quantizer or compressor's minimum and maximum value of amplitude would have been given as -5 volt and +5 volt. Value of A would have also been given. It is equal to 100. We need to find out the quantizer output for the given input, and those inputs are 30 millivolt and 3. So as a solution for 30 millivolt, normalize absolute input. Here X will going to represent your input signal and its normalized value would have been given as 0.3 divided by 5, or we could say the maximum value of our compressor or quantizer. So it would have been evaluated as 0.006. It basically lies in the range of 0 to 0.01. Where does this 0.01 comes? If we will going to calculate 1 over A, the value of A would have been given as 100. So the output or the value of 1 over A turns out to be 0.01. So it basically lies in this particular range. So we could say that the normalized input signal will going to lie in this particular range. So the compressor characteristics or the output of the compressor would have been calculated by this particular equation. A times of normalized signal value over 1 plus ln of A sine of S, since normalized signal value will lie in between 0 and 1 by A. So the normalized output of our given signal would have been calculated as 100 times of 0.006 over 1 plus ln of 100. This turns out to be 0.6 upon 5.605. If we are going to calculate 1 plus ln of 100, the value of ln of 100 will be equal to 4.606 plus 1 will be having 5.605. So which turns out to be 0.107. So this is our final outcome. Please keep in mind that this is the normalized value of our signal. So what will be the actual value of our signal? That has to be calculated by normalized value of the signal into its maximum value. So that turns out to be 0.535 volt. So we could say that the output of our compressor for the given input signal 30 millivolt will be having this 0.535 volt as an outcome. So now we're going to discuss the second part. The normalized absolute input X would have been calculated as 3 over 5. That turns out to be 0.6 volt. Again, it is lying in the range of 0.01, or we could say that 1 over A to 1. So hence the normalized output would have been calculated by this particular equation, that is 1 plus ln of A times of normalized value of our input signal over 1 plus ln of A into sine of input signal. So this is lying in this range. We have used this particular formula to calculate the normalized compressor output. That turns out to be 1 plus ln times of 100 into 0.6 over 1 plus ln of 100. So this would have been calculated as 5.094 divided by 5.605. So the ratio turns out to be 0.909. Again, since this is the normalized value of our compressor's output, so the final output or the actual output turns out to be normalized value into the maximum value, that turns out to be 4.545 volt. So this is our final outcome. So now we're going to discuss our second non-linear compressor, that is our mu law. So what is this mu law of compounding? So this is again a non-linear compressor. So the compressor characteristics are continuous. Please keep in mind the mu law of compressor characteristics are continuous, where the A-Law's compressor characteristics is the piecewise, and it would have been given with the following function. The logarithmic compressor employed in American and Canadian telecommunication system. This we had already discussed that it has been used in American and Canadian telecommunication systems. The normalized output of our compressor would have been given as 1 plus ln times of mu of normalized value of input signal divided by ln into 1 plus mu sine of s, where s is our normalized signal. This is the sine of our input signal, and it would have been calculated in the similar manner that we have discussed earlier. That is, for positive value of signal, this sine of s value is +1, and for negative value of our signal, its value is -1, and for zero level of signal or zero value of our signal, its value is 0. Again, mu is a constant. Mod of s, this is basically represents the normalized value of our input signal, and y is the normalized value of our output signal or the compressor output. Mu is a parameter which is selected to give the desired compressor characteristics. Its value is also fixed. Generally, the value of mu is equal to 255. This is what we have discussed. S is the normalized input signal and y is the normalized output signal. And the sine function, again, the value of sine of s would have been calculated as -1, 0 or +1, depending upon whether our input signal is negative, 0 or positive. So now we're going to discuss a numerical based on our mu law of compounding. So in mu law, PCM quantizer has the input range from -5 volt to +5 volt. For mu is equal to 100, find the output of the quantizer for the inputs of 30 millivolt and 3 volt. So this is basically the question analogous to the previous one. Here also the quantizer input range would have been given as -5 volt to +5 volt, and the value of mu would have been given as 100, and we need to find out the value of the quantizer output for the inputs 30 millivolt and 3 volts. So for 30 millivolt, normalized absolute input would have been calculated as the value of the input signal divided by the maximum value of the compressor input range, that turns out to be 0.006, and hence the normalized output would have been obtained as y is equal to 1 plus ln mu times of normalized value of our input signal divided by ln into 1 plus mu sine of s. So it would have been calculated as 1 plus ln times of, at the place of mu we have put 100, and normalized signal strength we had already calculated as 0.006 over ln 1 plus 100. So that turns out to be 0.4891 divided by 4.615. That turns out to be 0.1059. Again, we need to understand that this is the normalized value of our quantizer output. So in order to calculate the exact signal strength, we have to multiply it with the maximum value, that is 5 volt. So the actual output turns out to be 5 times of 0.1059. That turns out to be 0.5299 volts. So this is our mu law of quantizer or mu law of compressor output related to the input value 30 millivolt. That means when we're going to apply 30 millivolt inputs at the input side of our compressor, the output will be equal to 0.5299 volt. And similarly, we could calculate for 3 volt signal. So the normalized value of our input signal would have been calculated as 0.6 volt. So the normalized output would have been calculated as, or again with the same characteristics. So y turns out to be 1 plus ln times of 100 into 0.6 divided by 1 plus 100. So this would have been calculated as 0.8907. So again, this is the normalized value of outcome. So the actual output turns out to be 5 times of 0.8907. That turns out to be 4.4538 volt. So this is the finalized output of our numerical problem. That is, when we are going to apply 3 volt at the input of our compressor, the final output will be 4.4538 volts. So this particular figure shows the comparison between A-Law and mu-law. So this is the curve in between normalized input signal value and the normalized compressor output. So this particular purple color figure is signifies our mu law of compounding characteristics, where the value of mu is equal to 255, as we had already mentioned that it is the standard value. And this orange color curve shows the A law characteristics. The standard value of A will be 87.56. So we could say that when the normalized signal value is increasing, the normalized compressor output would have also been increasing, but its value is quite higher at lower values, and they are touching when normalized signal strength will almost equivalent to 0.7, and after that the input output levels will almost the same. So although both are non-linear compressors, but if we have to precisely say which one is better and which one is inferior, then we could say that below the value of 0.7, the signal to quantization noise ratio will be slightly better in A law of compounding in comparison to mu law of compounder. Although both are good and both are standard formats which have been used at different parts of the world. So now we're going to discuss the importance of compounding. So obviously there is a wide variety of audio transmission systems that has been using A-law of compounding and mu-law of compounding for the data rate reduction with good audio quality. Since it is our compression mechanism, so obviously we wanted that with the help of lower number of bits, we could have been passed larger amount of information with high signal to noise ratio. So both these methods, A-law and mu-law of compounding, do the same task for us. So the compression achieved by both the A-law and the mu-law of coding is the result of utilizing the logarithmic characteristics, as we had already discussed while discussing their equation, that how we're going to compress our signals. So they would have been actually being used for human auditory systems, or they are being used for compressing the human speech signals, where the fewer bits of precisions are required for larger signals than the smaller ones. So they are basically performing both the tasks. They are improving the signal to noise ratio for lower amplitude value of our signal, and side by side they are also using lesser number of bits to pass our information signal. So the logarithmic transfer function would have been implemented with a piecewise linear approximation. I mean, at shorter duration of a normalized input signal, its value is continuous. Otherwise, as a whole, if we have to monitor that, they are piecewise. So this is all about A-law and mu-law of compounding. These are the references that we have referred while creating this video. Thank you very much for your patient hearing.